Your cache was working perfectly. For hours, it absorbed millions of requests. Database load stayed low, page loads stayed fast. Then, at 8 p.m. peak traffic, one cache key expired. In the 200 milliseconds before any request could repopulate it, 47,000 requests hit your database simultaneously. The query that normally took 30 milliseconds took 18 seconds. Your platform served 503s for 11 minutes. One expired cache key. That's the thundering herd, and it's entirely self-inflicted. Day 7 was TTL, how you expire stale data. Set an expiry, refetch when it fires. Simple. Day 8 asks, what happens at the exact moment TTL fires for a key that 10,000 requests are waiting on? The cache doesn't fail. TTL works exactly as designed. That's the problem. Walk through what actually happens. A popular cache key expires. TTL elapsed. 10,000 concurrent requests all get a cache miss simultaneously. Every one of them goes to the database. Instead of one query, you get thousands at the exact moment your cache was supposed to absorb them. The database is overwhelmed. Responses slow or fail. The cache eventually repopulates, but the damage is done. This is different from a traffic spike. The traffic was already there being handled. TTL expiry is the trigger that routes all of it to origin at once. Think of it like a concert ending. 20,000 people handled fine for 2 hours because everyone was seated. The moment the lights come on, everyone moves simultaneously through the same 3 doors. Your cache is the venue. TTL expiry is the lights coming on. 3 solutions. Solution 1, the distributed mutex. The first request to get a miss acquires a lock and fetches from the database. Every other request waits for the lock, then reads from the freshly populated cache. One database query. 1. The downside, requests queue behind the lock. If the fetch is slow, everything waits. But a slow queue is far better than 10,000 simultaneous queries tearing through your database. Think single stall bathroom in a busy office. One person at a time. Everyone queues outside. Slightly slower, but nobody tries to share the stall. The queue is the cost. 10,000 people forcing the door simultaneously is the alternative. Solution 2. Probabilistic early recompute, PER. Before TTL expires, randomly start refreshing early. As expiry approaches, a request calculates an increasing probability that it should refresh in the background, while still serving the current cached value. The key never fully expires under load. No locking, no queue. The cache silently refreshes before anyone notices it's stale. Like a baker who starts the next batch while there are still a few loaves on the shelf. Not when it's empty. Customers never see an empty display. The bread never expires from their perspective. Solution 3. Staggered TTLs. Add random jitter to every expiry. TTL equals base TTL plus a random offset, 0 to 30 seconds. This desynchronizes expiry across keys. It doesn't prevent a single key from having a miss, but it prevents thousands of keys from expiring at the same moment and triggering correlated stampedes across the whole system. No single solution covers everything. PER for hot read keys, high volume, cheap refresh. You never want them to expire cold. Mutex for expensive computations. You never want parallel duplicate queries racing to the database. Staggered TTLs everywhere. Prevents mass correlated expiry events from creating system-wide load spikes. This isn't hypothetical. A social media company cached its trending topics list. Heavily read, embedded in every page load. Refreshed by a background job every minute. TTL set to 60 seconds. 8 p.m. Peak traffic. The cache key expires. In the 200 millisecond window before any request can repopulate it, 47,000 requests hit the database simultaneously. The query that normally took 30 milliseconds took 18 seconds under that load. App servers timed out waiting for the trending topics response. That endpoint was on every page. 503s for 11 minutes. Root cause, one expired cache key. Fix was 3 changes applied in parallel. A distributed mutex, only one database fetch at a time. Everyone else reads from cache once it's populated. TTL jitter, plus or minus 15 seconds around the base 60-second TTL, desynchronizes expiry from peak traffic windows. A background refresh job that preemptively refetched at 45 seconds before the TTL fired. The key was never allowed to go cold again. The thing that surprises people when they first see this in production, the thundering herd, is a reminder. The cache miss is the dangerous event, not the traffic spike. Engineers design for what if we get 10 times traffic, rarely for what if our cache has a 200 millisecond cold window at peak load. The second scenario can be more damaging, and it's entirely self-inflicted. A cache that expires synchronously under high concurrent load is a scheduled availability incident, not if, when. TTL is designed to make your cache temporarily fail. That's the point of TTL. The question is whether you've designed for what happens when it does. Treat TTL expiry as a production event to design around, not a background implementation detail. Set a TTL. Know when it fires. Know what your database sees when it does. Have a plan. The thundering herd isn't caused by too much traffic. It's caused by all that traffic suddenly losing its protection at once. Don't just set a TTL. Design for what happens when it fires. One action before you go. Find one hot cache key in your system. What's the TTL? What does your database see if that key expires under peak load right now? If you don't know, that's the question to answer this week. Next up, day 9. A slow database caused by a thundering herd is one of the classic cascade triggers. Day 9 is cascading failures. How one degraded service becomes total system failure and the pattern that stops it. See you there.